Howdy, this video is on gases and the ideal gas law. Gas is an important phase of matter. We're surrounded by gases, so gases are important. The ideal gas law and its assumptions yield relatively accurate descriptions of gases under normal circumstances, so the ideal gas law is also fairly important. After watching this video, you should be able to describe what gases are like at the atomic level and macroscopically. You should be able to describe the assumptions of the ideal gas law. You should be able to use the ideal gas law equation to calculate pressure, volume, number of moles, or temperature. And so if we think about a gas, this is kind of what it looks like. This is actually a decent simulation of water vapor at 1 atmosphere. Now, it's been slowed down a lot. 1 second in this movie corresponds to less than a picosecond. Remember, at the atomic level, things move really, really fast because they're really, really slow. But if we look at this movie, a couple of things that we should note is that, in general, gases are composed of free space. Lots and lots of free space. A lot of representations for gases that you might see probably have too many particles. In general, gases have a lot of free space. Gases can expand infinitely. Gases occupy containers uniformly and completely. Gases diffuse and mix rapidly. And so looking at the gas, we see a lot of free space, and so we can imagine that the intermolecular forces are negligible. And so for most of these gas particles, they don't seem to be interacting. You do find a couple, if you look carefully, that are interacting, but in general, gas particles don't interact, so intermolecular forces are negligible. Because the gas is composed mostly of mostly of free space, then we can argue that in general the volume of the gas particles themselves is negligible. And so those are actually the two assumptions for the ideal gas law. Intermolecular forces are negligible, the volume of the gas particles themselves are negligible. Gases can be monatomic or can be polyatomic. And so the noble gases are single atoms floating around. You can also have polyatomic gases: hydrogen gas H2, nitrogen gas N2, ammonia, carbon monoxide, oxygen gas, fluorine gas, chlorine gas, and carbon dioxide. And you should know these gases, these common gases. And so if you see a question about oxygen gas, you have to know that it is O2. If you cool a gas low enough, it will condense. All gases do condense when they're cooled. Now, if you look at helium, it's got the lowest boiling point of these gases of 4 Kelvin. Helium actually has the lowest boiling point of any element, and so it's a noble gas, so the only intermolecular force it has is London dispersion. It's very light, and so it has very weak London dispersion. Helium is so light that helium gas actually flies off the planet, out of the atmosphere. And so we're constantly losing helium. Helium's produced from radioactive decays underground, and so we do get some helium that way. If we think about the air around us, the composition of dry air at sea level, about 80% is N2, about 20% is O2. You got a little bit of argon, a little bit of CO2. It's also kind of interesting. You can imagine that the atmospheric pressure is just the sum of the masses of the weight of all the gas above you. And so what that means is the atmospheric pressure on top of a mountain is actually less than the atmospheric pressure in a valley. And so Mount Everest is 29,000 feet above sea level, and so its atmospheric pressure is 240 torr, whereas New York is about 10 feet above sea level, has atmospheric pressure of 760. Now, we saw previously that a liquid boils when the external pressure equals the vapor pressure. And so notice that the boiling point of water is 70 degrees Celsius on Everest, but it's 100 degrees Celsius in New York at sea level. So we can think about pressure as a sum of the weights of the gases above us. Pressure is also a result of the gas particles hitting the side of the container. And so both ways we can think about pressure. Now, when this can is just sitting, it's got gases inside, and so the gas inside is hitting the inside walls of the container, pushing out. Gas on the outside is hitting the walls of the container, pushing it in. Now, this is an aspirator here, and if we remove some of the gas from the inside, then we don't have as many particles hitting the inside walls of the container, and so nothing to oppose the outside walls of the container. And so what's going to happen is it collapses. Now, some people want to think that we're sucking the can in, but that's not what's happening. What's happening is we're removing the gas particles from the inside, and so the pressure from the outside has nothing to stop it from crushing the can. Another way we can do this is if we fill this pop can with a little bit of water, and then we boil the water, producing steam. And so when we have just steam in the can, if we put that into an ice bath, the steam will condense back to water, and so we'll have very few gas particles inside, and the can should crush.
A small amount of liquid water is placed in a can and boiled. The can fills with water vapor. Quickly inverting the can into ice water causes that vapor to condense, and atmospheric pressure crushes the can.
Kind of cool. And again, all that's happening is we're removing gas particles from the inside, and so there's nothing to stop the outside gas particles from crushing the can. That's kind of cool. You might think, okay, so that's fine. That's a pop can. That's made of aluminum. Is there something bigger? Could we do something like a 50-gallon drum? And so we do the same thing. We add some water. We then boil the water, producing steam. And so we want the steam to fill the 50-gallon drum, pushing out the gas particles. And then after we've produced a lot of steam, we will close the 50-gallon drum, sealing it. And then if we get the 50-gallon drum cold, the steam will condense into the liquid, and then we'll have a low pressure inside. And so then external pressure can actually cause the 50-gallon drum to collapse. Now, it actually takes a little bit of time to get the can cool because, it's a pretty big piece of metal. And so right now he's putting it in a bath with some ice water and putting some ice on top. Again, what this should cause is for the water vapor to condense in the liquid water, and so we'll have a low pressure inside the 50-gallon drum. Kind of cool, just from the external gas pressure. So a 50-gallon drum, that's cute. And then you could ask yourself, well, what about something bigger? So what about a tanker car? And evidently this actually happened where someone cleaned a tanker car, closed all the valves, went away, and then because they steam cleaned it, the steam eventually condensed in the liquid. You have a lack of pressure on the inside, and the external pressure just caused that tanker car to collapse. So we can actually characterize gases by volume, temperature, number of moles, and pressure, and we can model it using what's referred to as ideal gas law, PV equals nRT. And so pressure times volume equals number of moles times the gas constant times temperature. Now, it's very important that you remember that we always want to put the temperature in Kelvin, the volume in liters. N is the number of moles of the gas. Pressure, we can actually use a few different units. And the gas constant, there's also like 5 versions of the gas constant. And so depending on which unit you're using for pressure determines which gas constant you'll use. And so if the pressure is atmospheres, you'd use this gas constant. If the pressure is in bar, if the pressure is in kilopascals, if the pressure is in torr. And so you just use the appropriate gas constant based on the units of the pressure. Now, it's really kind of cool. If you look at the ideal gas law, you notice nowhere does it indicate the type of gas. All right, so you're looking at pressure, volume, number of moles, gas constant, and temperature. Nowhere does it say how many or what gas you're looking at. And so ideal gas law is independent of the type of gas. As I mentioned at the beginning, for ideal gas law, we assume intermolecular forces are negligible, and we assume the volume of the gas particles are negligible. And we can make those assumptions because for a gas, it's mostly empty space. Now, at low temperature, we know that all gases will condense. And so ideal gas law does break down at low temperature. At high pressure, you have a lot of gas particles, and so ideal gas law breaks down at high pressure. Now, there were 3 laws before the ideal gas law. There was Boyle's law, Charles' law, Avogadro's law. Now, all three of these are incorporated into the ideal gas law. And so you notice that Boyle's law, V is inversely proportional to P. Got it. For Charles' law, V and T are proportional. Well, we got it. And for Avogadro's law, V and N are directly proportional. We got it. And so ideal gas law incorporates all three, Boyle's, Charles, and Avogadro's law. And to me, it's important that you're able to use and apply the ideal gas law. And so Boyle's law says that volume is inversely proportional to pressure if the number of moles and temperature are constant. And so if we push down this plunger, we're reducing the volume. Now, the gas particles are going to hit the sides of the container more often if it's in a smaller volume, and that will cause the pressure to increase. And so volume and pressure inversely proportional as long as the number of moles and temperature are constant.
A decrease in the volume of a gas sample results in an increase in pressure because the gas particles will hit the walls of the container more often.
Pretty straightforward. And again, just think about pressures due to collisions of the gas with the walls of the container. More collisions give you higher pressure. Or even if the collisions have more kinetic energy, you'll get higher pressure.
When the gas in this cylinder is compressed at constant temperature, the gas pressure increases as the volume decreases. Robert Boyle, experimenting with air, found that the product of the pressure times the volume is a constant at constant temperature. Dividing through by the pressure, we see that volume is linearly related to the reciprocal of the pressure. These pressure-volume relationships are expressed by Boyle's law.
And so Boyle's law, as long as the number of moles and temperature are independent, pressure is inversely proportional to volume. Or you can say volume is inversely proportional to pressure. It's easiest to think about, if you reduce the volume, the particles will hit the sides of the container more often, causing the pressure increase. Charles' law says that if the number of moles and pressure are constant, then the volume is directly proportional to temperature. And so in this sealed syringe, if the piston goes up or down, it's going to have a constant pressure because the pressure is going to be from the atmospheric pressure. And so the atmospheric pressure inside the syringe. And it's sealed so the number of moles are constant. And so for the sealed syringe, number of moles are constant, pressure is constant. Now, if we warm up this ice bath, then we can change the temperature of the gas. And if we warm up the ice bath, what we're doing is we're going to give the particles more kinetic energy. Temperature is basically a measure of kinetic energy at the atomic level. And so if we give the particles more kinetic energy, they'll hit the sides of the container more often because they're moving faster and with more force. And so that will actually cause the plunger to move out. And so we'll see that volume is directly proportional to temperature.
Temperature and volume are directly related. As heat is added to a sealed syringe, the volume of the air in the syringe increases. A plot of gas temperature and volume demonstrates that the relationship between them is linear. If we extrapolate the line down to a temperature of absolute zero, in principle, the gas has no volume.
And so for an ideal gas, the temperature at 0 Kelvin, the volume at 0 Kelvin is 0. But we know that as we cool down a gas, eventually it's going to start to condense, and so it will stop behaving ideally. For an ideal gas, volume at 0 Kelvin is 0, but again, no gas will be ideal at that low of temperature. As you lower the temperature, gases become less ideal. And so we see that volume and temperature linearly proportional. Again, gases, before they get down to 0 Kelvin, will stop behaving ideally. So eventually, hydrogen will stop behaving ideally. Oxygen will stop behaving ideally. And so in the balloon, the pressure inside is basically due to atmospheric pressure. And so you'll have a constant pressure. The number of moles is constant because it's a sealed system. And so if we pour liquid nitrogen on our balloon, we can change the temperature of the gas inside without changing the pressure or the number of moles.
The Dewar flask or thermos contains liquid nitrogen at a temperature of 77 kelvins. The balloon has been blown up with air.
And so by lowering the temperature, you're removing some kinetic energy from the gas particles, so they're moving slower. They hit the sides of the container with less force, and so that causes the volume to reduce because the pressure is constant. As the gas particles start warming up again, then the balloon starts to expand into its original size. And so from Charles' law, we see that volume is directly proportional to temperature as long as we keep number of moles and pressure constant. For Avogadro's law, it says the volume is proportional to the number of moles as long as we keep temperature and pressure constant. And so if we have two balloons and one balloon has twice as many particles, then that should be twice the volume as long as pressure and temperature are the same. This one's kind of cool. So we have H2 and O2, so 8 molecules of H2, 4 molecules of O2, and so the 4 molecules of O2 should have half the volume of the H2. When these guys will react, we'll form 8 molecules of H2O. Now, if you have 8 molecules of H2O, they should have the same volume as the 8 molecules of H2. Because again, according to ideal gas law, all that matters is the number of particles, not the type of gas.
Quantity and volume are directly related. If we take 8 molecules of H2 and combine them with 4 molecules of O2, we get 12 molecules and a combined volume. If we then react the mixture, we end up with 8 molecules of gaseous H2O, which occupies the same volume as 8 molecules of any other gas.
And so if temperature and pressure are constant, then the volume is directly proportional to the number of moles. And so we see Avogadro's law, volume is directly proportional to N. Charles' law, volume is directly proportional to T. Again, all three laws, Boyle's, Charles, and Avogadro's law, are incorporated into the ideal gas law. So an interesting question would be, if the temperature of a gas is doubled while its volume is kept constant, what happens to the pressure? And so if we think about the ideal gas law, if we doubled the temperature in Kelvin, then the pressure should double. Remember, pressure is just a result of particles hitting the sides of the wall of the container. If you double the temperature, they're going to be hitting the sides of the wall of the container more often and with more energy. If the temperature of gas is tripled in Kelvin, what happens to the volume? The volume will also triple. So volume and temperature are directly proportional. Now this one's a little bit more tricky. If the temperature of gas is quadrupled, 100 Celsius to 400 Celsius, while its pressure is kept constant, what happens to the volume? Now you got to be careful. Remember, for PV equals nRT, temperature always has to be in Kelvin. And so to do this one, we have to convert from Celsius to Kelvin first. And so you can convert from Celsius to Kelvin by adding 273 to the Celsius. And so 100 degrees Celsius is equal to 100 plus 273, 373 Kelvin. 400 Celsius is equal to 400 plus 273, 673 Kelvin. And so now we can use the Kelvin temperature. And so if we quadruple the temperature from 100 to 400, the volume, new volume, is going to be 1.8 times the old volume because, again, you have to convert to Kelvin. So properties of gases, a lot of free space. They can expand infinitely. Gases occupy containers uniformly and completely. They diffuse and mix rapidly. And so the assumptions for ideal gas law are consistent with that. We assume intermolecular forces are negligible and the volume of the gas particles themselves are negligible. Again, looking at it, gases are mostly empty spaces, and so typically those assumptions are pretty good. And so ideal gases behave most ideal at high temperature, where we know that intermolecular forces are not very strong, and at low pressure, when we don't have a lot of gas particles. And so ideal gas law, PV equals nRT, can fairly accurately calculate properties for gases under normal conditions, and is more accurate the higher the temperature and the lower the pressure. I hope that was helpful.